A cold seep, sometimes called a cold vent, is an area of the ocean floor where hydrogen sulfide, methane and other hydrocarbon-rich fluid seepage occurs, often in the form of a brine pool. Cold does not mean that the temperature of the seepage is lower than that of the surrounding sea water. On the contrary, its temperature is often slightly higher. The cold is relative to the near-boiling conditions of a hydrothermal vent. Cold seeps constitute a biome supporting several endemic species. Cold seeps develop unique topography over time, where reactions between methane and seawater create carbonate rock formations and reefs. These reactions may also be dependent on bacterial activity. Ikaite, a hydrous calcium carbonate, can be associated with oxidizing methane at cold seeps. Types of cold seeps can be distinguished according to the depth, as shallow cold seeps and deep cold seeps. Cold seeps can also be distinguished in detail as follows: oil, gas seeps, methane seeps, gas hydrate seeps, brine seeps of forming brine pools, pockmarks, mud volcanoes, formation and ecological succession. Cold seeps occur over fissures on the seafloor caused by tectonic activity. Oil and methane seep out of those fissures, get diffused by sediment, and emerge over an area several hundred meters wide. Methane, CH4, is the main component of what we commonly refer to as natural gas. But in addition to being an important energy source for humans, methane also forms the basis of a cold seep ecosystem. Cold seep biota below 200 meters typically exhibit much greater systematic specialization and reliance on chemoautotrophy than those from shelf depths. Deep sea seeps sediments are highly heterogeneous. They sustain different geochemical and microbial processes that are reflected in a complex mosaic of habitats inhabited by a mixture of specialist, heterotrophic and symbiont-associated, and background fauna. Chemosynthetic communities. Biological research in cold seeps and hydrothermal vents has been mostly focused on the microbiology and the prominent macroinvertebrates thriving on chemosynthetic microorganisms. Much less research has been done on the smaller benthic fraction at the size of the myofauna, less than 1 mm. Community composition's orderly shift from one set of species to another is called ecological succession. The first type of organism to take advantage of this deep-sea energy source is bacteria, aggregating into bacterial mats at cold seeps. These bacteria metabolize methane and hydrogen sulfide, another gas that emerges from seeps, for energy. This process of obtaining energy from chemicals is known as chemosynthesis. During this initial stage, when methane is relatively abundant, dense mussel beds also form near the cold seep, mostly composed of species in the genus Bathymodeolus. These mussels do not directly consume food. Instead, they are nourished by symbiotic bacteria that also produce energy from methane. Similar to their relatives that form mats, chemosynthetic bivalves are prominent constituents of the fauna of cold seeps and are represented, in that setting, by 5 families: Solomyidae, Lucinidae, Vesicomyidae, Thiosiridae, and Mytillidae. This microbial activity produces calcium carbonate, which is deposited on the seafloor and forms a layer of rock. During a period lasting up to several decades, these rock formations attract sibiglin tube worms, which settle and grow along with the mussels. Like the mussels, tube worms rely on chemosynthetic bacteria, in this case, a type that needs hydrogen sulfide instead of methane, for survival. True to any symbiotic relationship, a tube worm also provides for their bacteria by appropriating hydrogen sulfide from the environment. The sulfide not only comes from the water, but is also mined from the sediment through an extensive root system. A tubeworm bush establishes in the hard carbonate substrate. A tubeworm bush can contain hundreds of individual worms, which can grow a meter or more above the sediment. Cold seeps do not last indefinitely, as the rate of gas seepage slowly decreases. The shorter-lived, methane-hungry mussels, or more precisely, their methane-hungry bacterial symbionts, start to die off. At this stage, tubeworms become the dominant organism in a seep community. As long as there is some sulfide in the sediment, the sulfide mining tubeworms can persist. Individuals of one tubeworm species, Lamellibrachia luimesi, have been estimated to live for over 250 years in such conditions. Comparison with other communities. Cold seeps and hydrothermal vents are communities that do not rely on photosynthesis for food and energy production. These systems are largely driven by chemosynthetic-derived energy. Both systems share common characteristics such as the presence of reduced chemical compounds, H2S and hydrocarbonates, local hypoxia or even anoxia, a high abundance and metabolic activity of bacterial populations, and the production of autochthonous organic material by chemo or autotrophic bacteria. Both hydrothermal vents and cold seeps show regularly highly increased levels of metazoan biomass in association with a low local diversity. This is explained through the presence of dense aggregations of foundation species and epizoic animals living within these aggregations. Community-level comparisons reveal that vent, seep and organic fall macrofauna are very distinct in terms of composition at the family level, although they share many dominant taxa among highly sulfidic habitats. However, hydrothermal vents and cold seeps differ also in many ways. Compared to their more stable cold seeps, vents are characterized by locally high temperatures, strongly fluctuating temperatures, pH, sulfide and oxygen concentrations, often the absence of sediments, a relatively young age, and often unpredictable conditions, such as waxing and waning of vent fluids or volcanic eruptions. Unlike hydrothermal vents, which are volatile and ephemeral environments, cold seeps emit at a slow and dependable rate, likely owing to the cooler temperatures and stability. Many cold seep organisms are much longer lived than those inhabiting hydrothermal vents. End of cold seep community. Finally, as cold seeps become inactive, tubeworms also start to disappear, clearing the way for corals to settle on the now exposed carbonate substrate. The corals do not rely on hydrocarbons seeping out of the seafloor. Studies on Lophelia pertusa suggest they derive their nutrition primarily from the ocean surface. Chemosynthesis plays only a very small role, if any, in their settlement and growth. While deep-water corals do not seem to be chemosynthesis-based organisms, the chemosynthetic organisms that come before them enable the coral's existence. This hypothesis about establishment of deep-water coral reefs is called hydraulic theory. Distribution. Cold seeps were discovered in 1983 by Dr. Charles Paul on the Florida Escarpment in the Gulf of Mexico at a depth of 3,200 meters, 10,500 feet. Since then, seeps have been discovered in other parts of the world's oceans. They have also been grouped into several biogeographic provinces: Gulf of Mexico, Atlantic, Mediterranean, East Pacific, West Pacific, and under an ice shelf in Antarctica. Those localities include the Monterey Canyon just off Monterey Bay, California, the Sea of Japan, off the Pacific coast of Costa Rica, in the Atlantic off of Africa, and in waters off the coast of Alaska. The deepest seep community known is found in the Japan Trench at a depth of 7,326 meters, 24,035 feet. with the recent discovery of a methane seep in the Southern Ocean. Methane seeps are now known in all oceans. Cold seeps are patchily distributed and they occur most frequently near ocean margins from intertidal to hadal depths. Methane seeps are common along continental margins in areas of high primary productivity and tectonic activity, where crustal deformation and compaction drive emissions of methane-rich fluid. Map of some cold seeps, marked with a star, in the Gulf of Mexico. Discoveries in the Gulf of Mexico equals. The chemosynthetic communities of the Gulf of Mexico have been studied extensively over the past 20 years, and communities first discovered on the upper slope are likely the best understood seep communities in the world. The history of the discovery of these remarkable animals has all occurred within the last 30 years. Interestingly, each major discovery was unexpected, from the first hydrothermal vent communities anywhere in the world to the first cold seep communities in the Gulf of Mexico. Communities were discovered in the eastern Gulf of Mexico in 1983 using the manned submersible DSV Alvin, during a cruise investigating the bottom of the Florida escarpment in areas of cold brine seepage, where they unexpectedly discovered tube worms and mussels. Paul et al. 1984. Two groups fortuitously discovered chemosynthetic communities in the central Gulf of Mexico concurrently in November 1984. During investigations by Texas A&M University to determine the effects of oil seepage on benthic ecology. Until this investigation, all effects of oil seepage were assumed to be detrimental. Bottom trawls unexpectedly recovered extensive collections of chemosynthetic organisms, including tube worms and clams. Kennicott et al. 1985. At the same time, LGL Ecological Research Associates was conducting a research cruise as part of a multi-year MMS Northern Gulf of Mexico Continental Slope Study. Galloway et al. 1988. Bottom photography, processed on board the vessel, resulted in clear images of vesicomyid clam chemosynthetic communities coincidentally in the same manner as the first discovery by camera sled in the Pacific in 1977. Photography during the same LGL MMS cruise also documented tube worm communities in situ in the central Gulf of Mexico for the first time, not processed until after the cruise. Boland, 1986. Prior to the initial submersible investigations and first-hand descriptions of Bush Hill, 27 degrees 47:02 N 91 degrees 30 minutes 31 seconds west. In 1986, Rosman et al. 1987a, McDonald et al. 1989b. The site was targeted by acoustic wipeout zones. A lack of substrate structure caused by seeping hydrocarbons. This was determined using an acoustic pinger system during the same cruise on the R.V. Edwin Link. The old one, only 113 feet, 34 meters, which used one of the Johnson Sea Link submersibles. The site is characterized by dense tubeworm and mussel accumulations, as well as exposed carbonate outcrops with numerous Gorgonian and Lophelia coral colonies. Bush Hill has become one of the most thoroughly studied chemosynthetic sites in the world. Distribution in the Gulf of Mexico equals. There is a clear relationship between known hydrocarbon discoveries at great depth in the Gulf slope and chemosynthetic communities, hydrocarbon seepage, and orthogenic minerals including carbonates at the seafloor. Sasson et al. 1993a and b. While the hydrocarbon reservoirs are broad areas several kilometers beneath the Gulf, chemosynthetic communities occur in isolated areas with thin veneers of sediment only a few meters thick. The northern Gulf of Mexico slope includes a stratigraphic section more than 10 kilometers, 6 miles, Thicken has been profoundly influenced by salt movement. Mesozoic source rocks from Upper Jurassic to Upper Cretaceous generate oil in most of the Gulf slope fields. Sasson al. 1993a and b. Migration conduits supply fresh hydrocarbon materials through a vertical scale of 6 to 8 kilometers, 4 to 5 miles, toward the surface. The surface expressions of hydrocarbon migration are referred to as seeps. Geological evidence demonstrates that hydrocarbon and brine seepage persists in spatially discrete areas for thousands of years. The timescale for oil and gas migration, combination of buoyancy and pressure, from source systems is on the scale of millions of years. Sasson, 1997. Seepage from hydrocarbon sources through faults towards the surface tends to be diffused through the overlying sediment. Carbonate outcroppings and hydrate deposits, so the corresponding hydrocarbon seep communities tend to be larger, a few hundred meters wide, than chemosynthetic communities found around the hydrothermal vents of the Eastern Pacific. McDonald, 1992. There are large differences in the concentrations of hydrocarbons at seep sites. Roberts, 2001, presented a spectrum of responses to be expected under a variety of flux rate conditions varying from very slow seepage to rapid venting. Very slow seepage sites do not support complex chemosynthetic communities. Rather, they usually only support simple microbial mats. Begiata sp. In the upper slope environment, the hard substrates resulting from carbonate precipitation can have associated communities of non-chemosynthetic animals, including a variety of sessile cnidarians such as corals and sea anemones. At the rapid flux end of the spectrum, fluidized sediment generally accompanies hydrocarbons and formation fluids arriving at the seafloor. Mud volcanoes and mud flows result. Somewhere between these two end members exists the conditions that support densely populated and diverse communities of chemosynthetic organisms. Microbial mats, Sibiglanid tube worms, Bathymodeoline mussels, Lucinid and vesicomyid clams, and associated organisms. These areas are frequently associated with surface and near-surface gas hydrate deposits. They also have localized areas of lithified seafloor, generally orthogenic carbonates, but sometimes more exotic minerals such as barite are present. The widespread nature of Gulf of Mexico chemosynthetic communities was first documented during contracted investigations by the Geological and Environmental Research Group, GERG, of Texas A&M University for the Offshore Operators Committee. Brooks al. 1986. This survey remains the most widespread and comprehensive, although numerous additional communities have been documented since that time. Industry exploring for energy reserves in the Gulf of Mexico has also documented numerous new communities through a wide range of depths, including the deepest known occurrence in the central Gulf of Mexico in Alaminos Canyon Bluff 818, at a depth of 2,750 meters, 9,022 feet. The occurrence of chemosynthetic organisms dependent on hydrocarbon seepage has been documented in water depths as shallow as 290 meters, 951 feet. Roberts al. 1990, and as deep as 2,744 meters, 9,003 feet. Allen, Personal Communication, 2005. This depth range specifically places chemosynthetic communities in the deepwater region of the Gulf of Mexico, which is defined as water depths greater than 305 meters, 1,000 feet. Chemosynthetic communities are not found on the continental shelf, although they do appear in the fossil record in water shallower than 200 meters, 656 feet. One theory explaining this is that predation pressure has varied substantially over the time period involved. Calendar and Powell 1999. More than 50 communities are now known to exist in 43 OCS blocks. Although a systematic survey has not been done to identify all chemosynthetic communities in the Gulf of Mexico, there is evidence indicating that many more such communities may exist. The depth limits of discoveries probably reflect the limits of exploration. Lack of submersibles capable of depths over 1,000 meters. 3,281 feet. McDonald et al. 1993 and 1996 have analyzed remote sensing images from space that reveal the presence of oil slicks across the north-central Gulf of Mexico. Results confirmed extensive natural oil seepage in the Gulf of Mexico, especially in water depths greater than 1,000 meters. 3,281 feet. A total of 58 additional potential locations were documented where seafloor sources were capable of producing perennial oil slicks. McDonald et al. 1996. Estimated seepage rates ranged from 4 barrels d. 0.64 cubic meters d. to 70 barrels d. 11 cubic meters d. compared to less than 0.1 barrel d. 0.016 m3 d. for ship discharges, both normalized for 1,000 square miles, 640,000 ac. This evidence considerably increases the area where chemosynthetic communities dependent on hydrocarbon seepage may be expected. The densest aggregations of chemosynthetic organisms have been found at water depths of around 500 m. 1,640 feet, and deeper. The best known of these communities was named Bush Hill by the investigators who first described it. McDonald et al. 1989b. It is a surprisingly large and dense community of chemosynthetic tubeworms and mussels at a site of natural petroleum and gas seepage over a salt diapir in Green Canyon Block 185. The seeps site is a small knoll that rises about 40 meters, 131 feet, above the surrounding seafloor in about 580 m. 1903 feet. Water depth equals stability equals. According to Sasson, 1997, the role of hydrates at chemosynthetic communities has been greatly underestimated. The biological alteration of frozen gas hydrates was first discovered during the MMS study, entitled Stability and Change in Gulf of Mexico Chemosynthetic Communities. Quote, it is hypothesized, McDonald, 1998b, that the dynamics of hydrate alteration could play a major role as a mechanism for regulation of the release of hydrocarbon gases to fuel biogeochemical processes and could also play a substantial role in community stability. Recorded bottom water temperature excursions of several degrees in some areas such as the Bush Hill site, 4 to 5 degrees Celsius at 500 m. 1640 feet depth, are believed to result in dissociation of hydrates, resulting in an increase in gas fluxes. McDonald et al. 1994. Although not as destructive as the volcanism at vent sites of the mid-ocean ridges, the dynamics of shallow hydrate formation and movement will clearly affect sessile animals that form part of the seepage barrier. There is potential of a catastrophic event where an entire layer of shallow hydrate could break free of the bottom and considerably affect local communities of chemosynthetic fauna. At deeper depths, greater than 1,000 meters, greater than 3,281 feet, the bottom water temperature is colder by approximately 3 degrees Celsius, and undergoes less fluctuation. The formation of more stable and probably deeper hydrates influences the flux of light hydrocarbon gases to the sediment surface. thus influencing the surface morphology and characteristics of chemosynthetic communities. Within complex communities such as Bush Hill, petroleum seems less important than previously thought. MacDonald, 1998b. Through taphonomic studies, death assemblages of shells, and interpretation of seep assemblage composition from cores, Powell et al., 1998, reported that, overall, seep communities were persistent over periods of 500 to 1,000 years and probably throughout the entire Pleistocene. Less than doubtful. Holocene. Some sites retained optimal habitat over geological time scales. Powell reported evidence of mussel and clam communities persisting in the same sites for 500–4,000 years. Powell also found that both the composition of species and trophic tiering of hydrocarbon seep communities tend to be fairly constant across time, with temporal variations only in numerical abundance. He found few cases in which the community type changed from mussel to clam communities, for example, or had disappeared completely. Faunal succession was not observed. Surprisingly, when recovery occurred after a past destructive event, the same chemosynthetic species reoccupied a site. There was little evidence of catastrophic burial events, but two instances were found in mussel communities in Green Canyon Block 234. The most notable observation reported by Powell, 1995, was the uniqueness of each chemosynthetic community site. Precipitation of orthogenic carbonates and other geologic events will undoubtedly alter surface seepage patterns over periods of many years. Although through direct observation, no changes in chemosynthetic fauna distribution or composition were observed at 7 separate study sites. MacDonald et al., 1995. A slightly longer period, 19 years, can be referenced in the case of Bush Hill, the first central Gulf of Mexico community described in situ in 1986. No mass die-offs or large-scale shifts in faunal composition have been observed, with the exception of collections for scientific purposes. Over the 19-year history of research at this site, all chemosynthetic communities are located in water depths beyond the effect of severe storms, including hurricanes, and there would have been no alteration of these communities caused from surface storms, including hurricanes. Biology equals. MacDonald et al., 1990, has described 4 general community types. These are communities dominated by vestimentiferous tube worms, Lamellibranchia c. F. Bahami and Escarpia spp. Mytilid mussels, seep Mytilid Iowa, Ib. and 3. and others. Vesicomyid clams, Vesicomia cordata and Calyptogena ponderosa, and infaunal Lucinida thiacirid clams, Lucinoma sp. or Thiazia sp. Bacterial matter present at all sites visited to date. These faunal groups tend to display distinctive characteristics in terms of how they aggregate, the size of aggregations, the geological and chemical properties of the habitats in which they occur and, to some degree, the heterotrophic fauna that occur with them. Many of the species found at these cold seep communities in the Gulf of Mexico are new to science, and remain undescribed. Individual lamellibranchid tube worms, the longer of 2 taxa found at seeps, can reach lengths of 3 meters, 10 feet, and live hundreds of years. Fisher et al., 1997. Bergquist et al., 2000. Growth rates determined from recovered marked tube worms have been variable, ranging from no growth of 13 individuals measured 1 year to a maximum growth of 9.6 centimeters per year, 3.8 in per year, in a Lamellibranchia individual. MacDonald, 2002. Average growth rate was 2.19 centimeters per year, 0.86 in per year. for the escarpia-like species and 2.92 cm per year, 1.15 in per year, for lamellibranchids. These are slower growth rates than those of their hydrothermal vent relatives. But lamellibranchia individuals can reach lengths 2 to 3 times that of the largest known hydrothermal vent species. Individuals of lamellibranchia sp. in excess of 3 meters, 10 feet, have been collected on several occasions, representing probable ages in excess of 400 years. Fisher, 1995. Westamentifran tube worm spawning is not seasonal and recruitment is episodic. Tube worms are either male or female. One recent discovery indicates that the spawning of female lamellibranchia appears to have produced a unique association with the large bivalve Acesta bulliesi, which lives permanently attached to the anterior tube opening of the tube worm, and feeds on the periodic egg release. Jarnagren al. 2005. This close association between the bivalves and tube worms was discovered in 1984. Boland, 1986. But not fully explained. Virtually all mature Acesta individuals are found on female rather than male tube worms. This evidence and other experiments by Jarnagren al. 2005 seem to have solved this mystery. Growth rates for methanotrophic mussels at cold seep sites have been reported. Fisher, 1995. General growth rates were found to be relatively high. Adult mussel growth rates were similar to mussels from a littoral environment at similar temperatures. Fisher also found that juvenile mussels at hydrocarbon seeps initially grow rapidly, but the growth rate drops markedly in adults. They grow to reproductive size very quickly. Both individuals and communities appear to be very long-lived. These methane-dependent mussels have strict chemical requirements that tie them to areas of the most active seepage in the Gulf of Mexico. As a result of their rapid growth rates, mussel recolonization of a disturbed seep site could occur relatively rapidly. There is some evidence that mussels also have some requirement of a hard substrate and could increase in numbers if suitable substrate is increased on the seafloor. Fisher, 1995. Two associated species are always found associated with mussel beds, the gastropod Bathonerita naticoidea and a small alvinocarid shrimp, suggesting these endemic species have excellent dispersal abilities and can tolerate a wide range of conditions. McDonald, 2002. Unlike mussel beds, chemosynthetic clam beds may persist as a visual surface phenomenon for an extended period without input of new living individuals because of low dissolution rates and low sedimentation rates. Most clam beds investigated by Powell, 1995, were inactive. Living individuals were rarely encountered. Powell reported that over a 50-year time span, local extinctions and recolonization should be gradual and exceedingly rare. Contrasting these inactive beds, the first community discovered in the central Gulf of Mexico consisted of numerous actively plowing clams. The images obtained of this community were used to develop length, frequency and live-dead ratios, as well as spatial patterns. Rosman al. 1987a. Extensive bacterial mats of free-living bacteria are also evident at all hydrocarbon seep sites. These bacteria may compete with the major fauna for sulfide and methane energy sources and may also contribute substantially to overall production. McDonald, 1998b. The white, non-pigmented mats were found to be an autotrophic sulfur bacteria Beggiatoa species, and the orange mats possessed an unidentified non-chemosynthetic metabolism. McDonald, 1998b. Heterotrophic species at seep sites are a mixture of species unique to seeps, particularly mollusks and crustacean invertebrates, and those that are a normal component from the surrounding environment. Carney, 1993, first reported a potential imbalance that could occur as a result of chronic disruption. Because of sporadic recruitment patterns, predators could gain an advantage, resulting in exterminations in local populations of mussel beds. It is clear that seep systems do interact with the background fauna, but conflicting evidence remains as to what degree outright predation on some specific community components such as tubeworms occurs. McDonald, 2002. The more surprising results from this recent work is why background species do not utilize seep production more than seems to be evident. In fact, seep-associated consumers such as galathide crabs and nerite gastropods had isotopic signatures, indicating that their diets were a mixture of seep and background production. At some sites, endemic seep invertebrates that would have been expected to obtain much if not all their diet from seep production actually consumed as much as 50% of their diets from the background. In the Atlantic Ocean, cold seep communities in the western Atlantic Ocean have also been described from a few dives on mud volcanoes and diapirs between 1,000 and 5,000 meters depth in the Bayard accretionary prism area, and from the Blake Ridge diapir off North Carolina. More recently, seep communities have been discovered in the eastern Atlantic, on a giant pockmark cluster in the Gulf of Guinea near the Congo Deep Channel, also on other pockmarks of the Congo margin, Gabon margin and Nigeria margin, and in the Gulf of Cadiz. The occurrence of chemosymbiotic biota in the extensive mud volcano fields of the Gulf of Cadiz was first reported in 2003. The chemosymbiotic bivalves collected from the mud volcanoes of the Gulf of Cadiz were reviewed in 2011. Cold seeps are also available in northern Atlantic Ocean. Map shows 3 localities there. Extensive faunal sampling has been conducted from 400 to 3,300 meters in the Atlantic equatorial belt, from the Gulf of Mexico to the Gulf of Guinea, including Bayard's accretionary prism, the Blake Ridge diapir, and in the eastern Atlantic from the Congo and Gabon margins and the recently explored Nigeria margin during Census of Marine Life Chess project. Of the 72 taxa identified at the species level, a total of 9 species or species complexes are identified as amphi-Atlantic. The Atlantic equatorial belt seep megafauna community structure is influenced primarily by depth, rather than by geographic distance. The bivalves Bathymodylae, within Mytylidae, species or complexes of species are the most widespread in the Atlantic. The Bathymodiolus boomerang complex is found at the Florida escarpment site, the Blake Ridge diapir, the Barbados prism and the Regab site of Congo. The Bathymodiolus childressi complex is also widely distributed along the Atlantic equatorial belt, from the Gulf of Mexico across to the Nigerian margin, although not on the Regab or Blake Ridge sites. The commensal pollinoid, Branchipollinocepensis, is known from the Gulf of Mexico, Gulf of Guinea and Barbados. Other species with distributions extending from the eastern to western Atlantic are gastropod Cordesia pravanoides, the shrimp Alvinocarus muricola, the galathiids Munidopsis gayeri and Munidopsis lavida, and probably the Holothura chirodota hehiva. There have been found cold seeps also in Amazon deep-sea fan. High-resolution seismic profiles near the shelf edge show evidence of near-surface slumps and faulting 20 to 50 meters in the subsurface, and concentrations, about 500 square meters, of methane gas. Several studies, e.g., Amazon Shelf Study, AMASEDS, LEPLAC, REMAC, Gloria, Ocean Drilling Program, indicate that there is evidence for natural seepage on the slope of the Amazon fan based on the incidence of bottom simulating reflections, BSRs, mud volcanoes, pockmarks, gas in sediments, and deeper hydrocarbon occurrences. The existence of methane at relatively shallow depths and extensive areas of gas hydrates have been mapped in this region. Also, gas chimneys have been reported, and exploratory wells have discovered subcommercial gas accumulations and pockmarks along fault plains. A sound geological and geophysical understanding of the Foz do Amazonas basin is already available and used by the energy companies. Exploration of new areas, such as potential seep sites off of the east coast of the U.S. and the Laurentian fan, where chemosynthetic communities are known deeper than 3,500 meters, and shallower sites in the Gulf of Guinea are need to study in the future. In the Mediterranean, the first biological evidence for reduced environments in the Mediterranean Sea was the presence of Lucinidae and vesicomyidae bivalve shells cored on the top of the Napoli mud volcano. 33 degrees 43 minutes 52 seconds north, 24 degrees 40 minutes 52 seconds east. Napoli is only a name of a seamount. It locates south of Crete. Located at 1,900 meters depth on the Mediterranean ridge in the subduction zone of the African plate. This was followed by the description of a new Lucinidae bivalve species, Lucinoma kazani, associated with bacterial endosymbionts. In the southeastern Mediterranean, communities of polychaetes and bivalves were also found associated with cold seeps and carbonates near Egypt and the Gaza Strip at depths of 500 to 800 meters. But no living fauna was collected. The first in situ observations of extensive living chemosynthetic communities in the eastern Mediterranean prompted cooperation between biologists, geochemists, and geologists. During submersible dives, communities comprising large fields of small bivalves, dead and alive, large Sibigulina tube worms, isolated or forming dense aggregations, large sponges, and associated endemic fauna were observed in various cold seep habitats associated with carbonate crusts at 1,700 to 2,000 meters depth. Two mud volcano fields were first explored, one along the Mediterranean ridge, where most of them were partially Napoli, Milano mud volcanoes, or totally Urania, Maidstone mud volcanoes, affected by brines, and the other on the Anaximander Mounds south of Turkey. The latter area includes the large Amsterdam mud volcano, which is affected by recent mud flows, and the smaller Kazan-Akula mud volcanoes. Gas hydrates have been sampled at the Amsterdam and Kazan mud volcanoes, and high methane levels have been recorded above the seafloor. Several provinces of the Nile deep sea fan have been explored recently. These include the very active brine seepage named the Men's Caldera in the eastern province, between 2,500 meters and 3,000 meters. The pockmarks in the central area along mid and lower slopes, and the mud volcanoes of the eastern province, as well as one in the central upper slope, North Alex area, at 500 meters depth. During these first exploratory dives, symbiont-bearing taxa that are similar to those observed on the Olympian and Anaximander mud fields were sampled and identified. This similarity is not surprising, as most of these taxa were originally described from dredging in the Nile fan. Up to 5 species of bivalves harboring bacterial symbionts colonized these methane and sulfide-rich environments. A new species of Sibigulinidae polychaete, Lamelybrachia anaximandri, the tubeworm colonizing cold seeps from the Mediterranean ridge to the Nile deep sea fan, has just been described in 2010. Moreover, the study of symbioses revealed associations with chemoautotrophic bacteria, sulfur oxidizers in vesicomyidae and Lucinidae bivalves and Sibigulinidae tubeworms, and highlighted the exceptional diversity of bacteria living in symbiosis with small mytilidae. The Mediterranean seeps appear to represent a rich habitat characterized by megafauna species richness, e.g., gastropods, or the exceptional size of some species such as sponges, Rhizoxanella pyrifera, and crabs, Chaetion mediterraneus, compared with their background counterparts. This contrasts with the low macro and megafaunal abundance and diversity of the deep eastern Mediterranean seep communities in the Mediterranean that include endemic chemosynthetic species and associated fauna differ from the other known seep communities in the world at the species level, but also by the absence of the large-size bivalve genera Calyptogena or Bathymodeolis. The isolation of the Mediterranean seeps from the Atlantic Ocean after the Messinian crisis led to the development of unique communities, which are likely to differ in composition and structure from those in the Atlantic Ocean. Further expeditions involved quantitative sampling of habitats in different areas, from the Mediterranean ridge to the eastern Nile deep-sea fan. Cold seeps discovered in the Sea of Marmara in 2008 have also revealed chemosynthesis-based communities that showed a considerable similarity to the symbiont-bearing fauna of eastern Mediterranean cold seeps. In the West Pacific, native aluminium has been reported also in cold seeps in the northeastern continental slope of the South China Sea, and Chen et al. 2011 have proposed a theory of its origin as resulting by reduction from tetrahydroxoaluminate Al. O4- to metallic aluminium by bacteria. Japan Deep-sea communities around Japan are mainly researched by Japan Agency for Marine Earth Science and Technology, JAMSTEC, DSV Shinkai 6500. Kaiko and other groups have discovered many sites. Methane seep communities in Japan are distributed along plate convergence areas because of the accompanying tectonic activity. Many seeps have been found in the Japan Trench, Nankai Trough, Ryukyu Trench, Sagami Bay and Suruga Bay, and the Sea of Japan. Members of cold seep communities are similar to other regions in terms of family or genus, such as Polychaeta, Lamelybrachia, Bivalvia, Solomyidae, Bathymodeolus in Mytilidae, Thiosiridae, Calyptogena in Vesicomyidae, and so forth. Many of species in cold seeps of Japan are endemic. In Kagoshima Bay, there are methane gas seepages called tagiri. Boiling Lamelybrachia satsuma live around there. The depth of this site is only 80 meters, which is the shallowest point Sibiglanidae living. L. Satsuma may be kept in an aquarium for a long period in one atmosphere. 2 aquariums in Japan are keeping and displaying L. Satsuma. An observation method to introduce it into a transparent vinyl tube is being developed. DSV Shinkai 6500 discovered vesicomyid clam communities in the southern Mariana Forearc. They depend on methane, which originates in serpentinite. Other chemosynthetic communities would depend on hydrocarbon origins, organic substance in crust. But these communities depend on methane originating from inorganic substances from the mantle. In 2011, was performed around the Japan Trench, which is epicenter of Tohoku earthquake. There are cracks, methane seepages and bacterial mats which were probably created by the earthquake. New Zealand off the mainland coast of New Zealand. Shelf edge instability is enhanced in some locations by cold seeps of methane-rich fluids that likewise support chemosynthetic faunas and carbonate concretions. Dominant animals are tube worms of the family Sibiglanidae and bivalves of families Vesicomyidae and Mytilidae. Bathymodeolus. Many of its species appear to be endemic. Deep-bottom trawling has severely damages cold seep communities, and those ecosystems are threatened. Depths down to 2,000 meters, including cold seeps, belongs among as yet unmapped topographic and chemical complexity of habitats. The scale of new species discovery in these poorly studied or unexplored ecosystems is likely to be high. In the East Pacific, in the deep sea, the COMARGE project has studied the biodiversity patterns along and across the Chilean margin through a complexity of ecosystems such as methane seeps and oxygen minimum zones, reporting that such habitat heterogeneity may influence the biodiversity patterns of the local fauna. Seep fauna include bivalves of families Lucinidae, Thiosiridae, Solomyidae, Acarax sp. and Vesicomyidae, Calyptogena gallardois, and Polychaetes lamlibrachia sp. and 2 other polychaete species. Furthermore, in these soft reduced sediments below the oxygen minimum zone off the Chilean margin, a diverse microbial community composed by a variety of large prokaryotes, mainly large multicellular filamentous megabacteria of the genera Theoploca and Begiata, and of macrobacteria, including a diversity of phenotypes, protists, ciliates, flagellates, and foraminifers, as well as small metazoans, mostly nematodes and polychaetes, has been found. Gallardo et al. 2007 argue that the likely chemolithotrophic metabolism of most of these mega and macrobacteria offer an alternative explanation to fossil findings, in particular to those from obvious non-literal origins, suggesting that traditional hypotheses on the cyanobacterial origin of some fossils may have to be revised. Cold seeps, pockmark, are also known from depths of 130 meters in the Hecate Strait, British Columbia, Canada. Unobvious fauna, also unobvious for cold seeps, has been found there, with these dominating species: sea snail Fusa triton oregonensis, anemone Metridium giganteum, encrusting sponges, and bivalve Solomyidae. Cold seeps with chemosynthetic communities along the USA Pacific coast occur in Monterey Canyon, just off Monterey Bay, California, on a mud volcano. There have been found, for example, Calyptogena clams, Calyptogena kilmeri, and Calyptogena pacifica, and foraminiferan Spiriplectamina biformis. Map of cold seeps in the Monterey Bay. Additionally, seeps have been discovered offshore Southern California and the inner California borderlands along several fault systems, including the San Clemente Fault, San Pedro Fault, and San Diego Trough Fault. Fluid flow at the seeps along the San Pedro and San Diego Trough Faults appears controlled by localized restraining bends in the faults. In the Antarctic, the first cold seep was reported from Southern Ocean in 2005. The relatively few investigations to the Antarctic deep sea have shown the presence of deep water habitats, including hydrothermal vents, cold seeps, and mud volcanoes. Other than the Antarctic benthic Deep Sea Biodiversity Project (ANDEEP) cruises, little work has been done in the deep sea. There are more species waiting to be described. Detection. With continuing experience, particularly on the upper continental slope in the Gulf of Mexico, the successful prediction of the presence of tubeworm communities continues to improve. However, chemosynthetic communities cannot be reliably detected directly using geophysical techniques. Hydrocarbon seeps that allow chemosynthetic communities to exist or modify the geological characteristics in ways that can be remotely detected. But the time scales of co-occurring active seepage and the presence of living communities is always uncertain. These known sediment modifications include 1. Precipitation of orthogenic carbonate in the form of micronodules, nodules, or rock masses. 2. Formation of gas hydrates. 3. Modification of sediment composition through concentration of hard chemosynthetic organism remains, such as shell fragments and layers. 4. Formation of interstitial gas bubbles or hydrocarbons. And 5. Formation of depressions or pockmarks by gas expulsion. These features give rise to acoustic effects such as wipeout zones, no echoes, hard bottoms, strongly reflective echoes, bright spots, reflection-enhanced layers, or reverberant layers. Behrens, 1988. Robertson Neureuther, 1990. Potential locations for most types of communities can be determined by careful interpretation of these various geophysical modifications, but to date, the process remains imperfect and confirmation of living communities requires direct visual techniques. Fossilized records. Cold seep deposits are found throughout the Phanerozoic rock record, especially in the late Mesozoic and Cenozoic. See for example Kame al. 2008. These fossil cold seeps are characterized by mound-like topography, where preserved, coarsely crystalline carbonates, and abundant mollusks and brachiopods. Environmental impacts. Major threats that cold seep ecosystems and their communities face today are seafloor litter, chemical contaminants and climate change. Seafloor litter alters the habitat by providing hard substrate where none was available before, by overlying the sediment, inhibiting gas exchange, and interfering with organisms on the bottom of the sea. Studies of marine litter in the Mediterranean include surveys of seabed debris on the continental shelf, slope, and bathyal plain. In most studies, plastic items accounted for much of the debris, sometimes as much as 90% or more of the total, owing to their ubiquitous use and poor degradability. Weapons and bombs have also been discarded at sea, and their dumping in open waters contributes to seafloor contamination. Another major threat to the benthic fauna is the presence of lost fishing gear, such as nets and long lines, which contribute to ghost fishing and can damage fragile ecosystems such as cold water corals. Chemical contaminants such as persistent organic pollutants, toxic metals, e.g., Hg, Cd, Pb, Ni, radioactive compounds, pesticides, herbicides, and pharmaceuticals are also accumulating in deep-sea sediments. Topography, e.g., presence of canyons, and hydrography, e.g., cascading events, play a major role in the transportation and accumulation of these chemicals from the coast and shelf to the deep basins, affecting the local fauna. Recent studies have detected the presence of significant levels of dioxins in the commercial shrimp Aristeus antennatus and significant levels of persistent organic pollutants in mesopelagic and bathypelagic cephalopods. Climate-driven processes and climate change will affect the frequency and intensity of cascading, with unknown effects on the benthic fauna. Another potential effect of climate change is related to energy transport from surface waters to the seafloor. Primary production will change in the surface layers according to sun exposure, water temperature, major stratification of water masses, for example, and this will affect the food chain down to the deep seafloor, which will be subject to differences in quantity, quality, and timing of organic matter input. As commercial fisheries move into deeper waters, all of these effects will affect the communities and populations of organisms in cold seeps and the deep sea in general. See also brine pool, chemosynthesis, chemotroph, DSV Alvin, hydrothermal vent. This article incorporates a public domain work of the United States government from references and CC by 2.5 from references and CC by 3.0 text from the reference. Further reading. Bright M. Plum C. Ryevitz L. A. Nikolov N. Martinez Arbazu P. and Kordzi E. and Golner S. 2010. Epizoic metazone myobenthos associated with tubeworm and mussel aggregations from cold seeps of the northern Gulf of Mexico. Deep Sea Research Part 2. Topical Studies in Oceanography 57. 21-23. 1982-1989. DOI 10.1016 J. DSR 2.2010.05.003. German C. R. Ramirez Ladreri, Baker M. C. Taylor P. A. and the Chess Scientific Steering Committee. 2011. Deepwater Chemosynthetic Ecosystem Research during the Census of Marine Life Decade and Beyond. A Proposed Deep Ocean Road Map. PLOS 168. E23259. DOI 10.1371. Journal. Pone. 002329. Lloyd K. G. Albert D. B. Biddle J. F. Chanton J. P. Pizarro O. and Tesker A. 2010. Spatial structure and activity of sedimentary microbial communities underlying Abegiata spp. Matina Gulf of Mexico hydrocarbon seep. PLOS 151. E8738. DOI 10.1371. Journal. Pone. 00083738. Metaxas A. and Kelly N. E. 2010. The larval supply and recruitment vary among chemosynthetic environments of the deep sea. Quote. PLOS 157. E11646. DOI 10.1371. Journal. Pone. 00114646. Rodriguez E. and Daly M. 2010. Phylogenetic relationships among deep-sea and chemosynthetic sea anemones. Actinos cyphiidae and Actinostolidae. Actiniaria. Mesimiaria. Quote. PLOS 156. E10958. DOI 10.1371. Journal. Pone. 001098. Subuet M. and Ola K. 1998. Biogeography. Biodiversity and fluid dependence of deep-sea cold seep communities at active and passive margins. Deep Sea Research Part 2. Topical Studies in Oceanography 45. 1-3. 517-567. DOI 10.1016. SO967-0645. 97. 00074EX. Vin. O. Runovich. K. Little. C. T. S. Nakram. H. A. 2014. Arboreal serpulid fauna from Volgan-Ryazanian. Latest Jurassic, earliest Cretaceous. Shelf sediments and hydrocarbon seeps from Svalbard. Geodiversitas. 36. 4. 527-540. DOI 10.5252 per grams 2014 N4A2. Retrieved 9 January 2014. Vin. O. Kuprianova. E. K. Keel. S. 2013. Serpulids. Annelida. Polychaeta. At Cretaceous to modern hydrocarbon seeps. Ecological and evolutionary patterns. Paleogeography, paleoclimatology, paleoecology. 390. 35-41. DOI 10.1016 J. Paleo. 2012.08.003. Retrieved 9 January 2014. Paul Yancey's Vents and Seeps page. Monterey Bay Aquarium Research Institute Seeps page. Science Daily News. Tubeworms in deep sea discovered to have record long lifespans.